The first part of section 2 talks about if a function is differentiable. That means, can you take a derivative of the function? So we're going to look at maybe what makes a function, what makes you able to take a derivative of a function, but also where are there spots where you won't be able to take a derivative. We're going to look at 3 examples in this video and then try to kind of summarize our findings here. We're going to look at 3 separate functions. The first is the absolute value of x minus 3, and if you think back to pre-calculus, the minus 3 is going to force the absolute value graph to shift to the right by 3. So we're going to count off by 1, 2, 3. This is now going to be where our vertex is, and it's going to go up like that and up like that. Okay, then we have 4 parts of our question to answer. Part A, what is the derivative of f as x approaches 3, but approaching 3 from the left-hand side? So what's going to happen, or what are the slopes as we get this way? Well, it's a line. The slopes are always going to be the same, and for that section the slope is -1. Part B is asking the same thing, but now from the right side. There the slopes would be +1. And then just a couple summary questions. Do you think the function is continuous? At 3, we know enough about this that yes, it is continuous. We can trace the entire function without lifting up our pencil, especially at the point 3. And is it going to be differentiable at x equals 3? So here we go back to our limit definition of what a derivative is. And we'd say from this side we have a certain slope, from this side we have a certain slope. They're not matching up. It's not a nice smooth change there. So we could, if you think of the definition of a tangent line, we might say, oh, we could have a tangent line that's going like that, or like that, or like that. Whenever that happens, when there's multiple ways to write maybe a tangent line, something that touches once, we're actually going to have to say that no, it is not differentiable. So here's one example where the function happens to be continuous, but it's not differentiable at a certain point, and we would call this a corner. Second example says, graph the function f of x equals x to the 2/3 power. We could go through and prove this a little bit. We actually learned how to do this in pre-calculus. Just for the sake of time on the video, I'm just going to draw it for you. It's going to do something like this, where almost like a square root function there, and it's going to be reflected over on that side as well. And so we're looking in part A at x approaching 0. What's happening to the derivative as we approach from the left and the right hand sides? So let's look at what happens as we approach from the left hand side. As we're coming like this, what are our slopes getting closer and closer to? We're going to write this in an informal notation. We might say as x approaches 0 from the left side, f prime will approach. Now what do you think the slopes are approaching here? It looks like they're becoming more and more negative, steeper or bigger number values in a negative fashion, and eventually we'd end up with negative infinity. Okay, and then if we do the same thing from the right hand side, so as x approaches 0 from the right, I'm sorry, that's not what I wanted. Let me erase here. F prime, what are the slopes approaching? So now we're looking at it from this way as we approach from the right hand side. Now they're becoming more and more positively sloped, a bigger number but positive. So we would say that it is going to approach infinity, as steep as we can get in a positive fashion. Now part B is actually going to give us the algebra derivative, and you will eventually know how to do this, but this is the derivative. What is the value of the derivative when x equals 0? If I were to plug a 0 in here, I would get something that is undefined, can't divide by 0. And so that's going to be a problem as well. So whenever you see the slopes approaching infinity or negative infinity from the left and right sides, that's going to be an issue. We call a shape like this a cusp. And our last example is the cube root of x, and I think we're somewhat familiar with this too. On the right side, it's going to kind of look like a square root function. The left side, kind of a flipped square root function. So that is the cube root of x. It is the inverse of x cubed, if that helps. And again, we're going to describe the derivative as x approaches 0 from the left and right hand side. So what's going on right at this point right there? We're going to write it out the same way, kind of informal limit notation. As x approaches 0 from the left, f prime is approaching. And what is that getting closer to? Okay, that's the question. And so as we come from the left-hand side, it's getting really, really steep, and if I could draw it perfectly, we would actually, at one point, we'd have a vertical tangent line going straight up. And so the slope right there would be positive infinity. And kind of the same thing as x approaches 0 from the right-hand side, what is f prime going to approach? So now we're going from this way towards 0. Again, at one point, we're going to have that vertical tangent again, and so the slope there would also approach positive infinity. So now, different than example 2, now they have the same sign, but they're both infinities. And that's also going to be an issue. Again, later on, you're going to have the tools to go from this to the derivative. This is the derivative of function f, and so if we were to plug a 0 in and say, well, what's the slope at 0, we would get something that is undefined again. Doesn't help us. So even though we end up with the same number, remember that infinity isn't really a number, that's going to cause an issue as well, and we call this a vertical tangent. And the three things that we just covered are kind of three problem areas, and that is kind of what is summarized in this paragraph right there. But those three things you should be familiar with. We'll go over some typical examples of those and how you should be looking for those in your homework for this section.